Good morning, friends. Today we will discuss about a very common problem about designing a LRU cache. So the concept of cache is very simple. Suppose we are going to fetch a lot of data from a from a distant source, for example, from a database or from a network or from a hard disk. In that case, if the we know that there might be a lot of latency induced by fetching the data from all these resources. But if we create a small cache in between, and if we can fetch that data, that most fetched data, we can store it into an intermediate cache. This can actually improve a lot of performance. So in that case, we don't need to fetch the data from these data sources, like for example, as we discussed, database, a hard disk, or network. And so the basic idea here is that we should be smart enough to design our cache in such a way that the most fetched data can be stored in the cache, which is much smaller in the size than the actual underlying data source. This will tremendously improve the latency or the performance of our application. This is actually employed in our multi-core CPU architecture at the moment. So as we know that by the advent, hardware has been improving by following the Moore's law that every 2 years it improves in the performance. So this was like introduced like long time back, I think more than 10-15 years back, when we had multi-core processors in our system. So the main idea was that our CPU can have multiple cores, so multiple core units here, and fetching the data from the main memory, it normally takes around 100 nanoseconds. But if we have got a lot of caches in between, for example, we have got L1 cache, L2 cache, and L3 cache, which are smaller in size than the main memory, but it can store some fetch data here. So instead of fetching all the data from main memory, if the data is already stored in the much nearer caches like L1, L2, and L3, the performance is much improved. For example, for fetching as just I think just by the heuristic I know that fetching the data from the main memory takes around 100 nanoseconds. Fetching from L2 is around 7 nanoseconds, and from L1 it's as less as 0.1, 0.1 or zero point 0.5 nanoseconds. And if the data is already in the register, it's almost instant. So this is the but the most important thing that we need to understand is that uh, these caches are small, much smaller than the main memory. So the data which can be stored, that should be very smart enough that it should always store the data which is most important, which can be first fetched most recently, or it is more likely to be fetched. That's why we say that the data structures like arrays are very cache friendly. What we mean by that is cache friendly, because for arrays we know that it's always stored in the contiguous area in the memory. We just need to know the root of the array address, and from there, if whatever index that has been provided, that would be next to it. That's why when the arrays are fetched from the CPU core for the data, all those the nearby elements of the array index or the array indices are already stored in the cache, so that the fetching of the data is very fast. That's why we say that the arrays are cache friendly. But in contrast to arrays, when you talk about say linked list, in linked list are not cache friendly, because each of the nodes are created randomly in the main memory or in the heap, and there it would be one node can be pointed in some location, and the next link of the node can be that node can be anywhere random. So there's no way we can actually find it immediately. We have to go through all the nodes to search for a particular node which we want to get the data from. That's why we say that linked lists are not cache friendly. So here the most important concept that we are going to discuss is about a cache hit and a cache miss. And we also want to ensure that to be cost effective and to enable efficient use of data, caches must be relatively small. This is what we have to ensure. So cache hit means that whenever we are trying to fetch the data, we already find in the cache, then it is called as cache hit. This will improve the performance. But if there is a cache miss, then there is no way we can find in the cache. Then we have to again go back to the underlying data source and get the data from there. So the cache miss are costly, but as soon as the cache miss happens, we have to actually put that data back into our cache and remove some data which has not been recently used. This is what the eviction policy of the cache comes. least recently used cache. For cache, we always have a defined capacity. I mean, it should be always less than. Is it little small, and it should be always less than the underlying data source, of course. That's why it will be having the best performance. So whatever the data which is not recently being used, only that can be evicted. Whenever we are hitting the capacity of our cache, so in that case, we have to evict or remove that data which has not been used recently. Say, for example, in our cache, we have got a capacity of 10 elements. And in those 10 elements that we are storing in the cache, that are the most recently fetched data. And we can say that if we maintain a linked list of that, if we just implement it as a linked list, so we can actually assume that at the head of the linked list, that is the most recently used, and that's why at the top of the head, and the least recently used should be at the bottom of the at the tail of that linked list. So if we have got a new item to be fetched and put into our cache, then to make the space for that extra 11th element, we have to remove the last element from the which is the least recently used element in from our linked list implements of the cache. We have to remove it from the last of it. So this is what LRU cache algorithm is. So as we explained about the problem now, so let's design an LRU cache. But this for the first follow up, for the first basic problem, we have to implement it the LRU cache by using the linked hash map, which is already provided in our Java API. After that, we will follow up that we will not use this Java provided API, and we will use our own implementation by using linked list and a simple hash map to implement the same, and should be also thread safe. So this is the design problem statement that we have to design our LRU cache. First starting with the linked hash map. So in this problem statement, we have got this interface here, which would be working as our LRU cache. As you can see, we have got custom hash table with key and value as generic types. And we should get the value by calling these three methods. It's very much similar to that how hash map is implemented. And then we have got two concrete classes in which the first one would be using as a linked hash map as our LRU cache. And in the second one, in the follow up, we would be using this, our own custom linked list node along with our own map version to implement the same, not using the linked hash map. So let me actually quickly go through the linked hash map API. So here in our Java package, I'm using Java 11. You can use whatever version that you are working on, but the idea of linked list hash map is quite similar in all the versions. So here, it's actually maintained using a hash table and linked list. So as I mentioned that before that, for the cache, we can have, if we implement a cache as a linked list, the most recently used can be marked as the head, and the least recently used be at the tail of that linked list. And whenever we want to evict any or remove any element, that would be from the tail of the linked list. So I think it's very much similar that how the linked hash map has been implemented in the Java APIs. So besides that, I mean, to maintain the state, it also uses hash table. That's why it's called linked hash map. It's a combination of linked list plus hash map. And this linked list is actually a doubly linked list as mentioned in the API documentation. Okay, so it actually maintains the insertion order as well as the access order. If you look at the constructor of it, so here I have it's actually mentioned that we can from least recently access to most recently access order. This kind of map is well suited to building LRU cache. That's why I mentioned that the linked hash map can be also used to implement our LRU cache. If you go through the constructor of it, so for all these constructors, if we just create like for linked list without any capacity or with some initial capacity or the load factors and all, by default it would be having a insertion order. It means that whatever, suppose if we have got 10 elements that we are going to insert in our linked hash map, it will follow the insertion order, which means that the first element which has been inserted, that would be following the same ordering. And for the 10th element which has been entered, it would be all following the same ordering. Whenever we want to whenever you want to iterate through our linked hash map, it will start from the first element which has been inserted, followed with, and the last element would be the 10th element which has been inserted. This is what we mean by insertion order. If we take a normal hash map, it is random. I mean, there is no iteration order guaranteed. But using linked hash map, by default, the insertion order is guaranteed. And I think for hash map, we already know about the concept of capacity and the load factor. Just to revise it, the capacity means by default the capacity is 16 and the load factor is 0.75. So 0.75 means it would be 12, or 75% of 16 is 12, which means that if this linked hash map has got the elements up to 12, then after that it has got a threshold of 12. It means that the capacity would be increased from 16 to 32. So this is what load factor means. I mean, it will automatically resize our hash map capacity. And as soon as, like, for 32, if it takes 75% of 32, it would be, I think, 24. In that case also, it would be whenever our cache size reaches 24, then again the capacity would be automatically increased from 32 to 64. So this is the idea of capacity and load factor. So in our LRU cache implementation, we don't want the insertion order, but we want the access order. This is where we have to use this particular constructor, in which we can specify the access order. By default, it would be insertion order, but if we want to mark it as access order, which means that whenever we are not following any insertion order, but the iteration should be done based on what is the least access, the most recently accessed element from our linked hash map, or the least access map. So let me actually expand it, and then it will be more clear. So initial capacity and load factor are same. Most important thing that we are interested in our LRU cache is this Boolean access order. Access order is this order mode: true for access order and false for insertion order. If I mark it as false, it will take the default behavior of insertion order, but we want to use the access order, because then only we can know that what is the latest and what is the least recently used entry that can be evicted or removed. So we'll be using this ordering mode as true. So guys, this was all about the problem statement first. So please try on your own to implement our LRU cache using the linked hash map. I have given enough hints about how to create it by using this constructor with access order as true. Please try it. In the next video, we'll see that how to solve it, and then we will follow up again the problem without using the linked hash map and using our own custom doubly linked list node and our concurrent hash map. So see you all in the next video.